In this ninth lecture, I want to talk about partial identification. So this is an area I was personally very skeptical about for a long time. I remember first seeing some of this stuff in, I think, 1990, when Mansky was beginning to work on this, and I didn't really think all that much of it at the time. And sort of even, I think, in 1998, I had dinner at some point with Ed Leamer and Mansky, and Ed Leamer was sort of questioning whether this bound stuff, as people called it at the time, was really going anywhere. And both of us didn't seem to think it was, and Mansky certainly couldn't convince us at the time. But I think actually we were probably wrong, and I think now this is actually a very important area. There's been a lot of interesting work done there. Sort of a lot of it starting with work by Mansky, but also a lot of very interesting applications by Tamer and co-authors. So in contrast to some of the earlier lectures where I felt much more much more confident sort of about what specifically people should know about these areas. Here, I think this is much more an area that's still very much in flux. And so what I want to do instead is just discuss at some length some examples that sort of show how so at least in my view, this is a very promising area. And then only towards the end, talk about some specific methods and issues and economic statistical issues that have come up, and some of which I think we sort of have some idea how to deal with, but some of which I'm sure we'll see further developments. So I mean, the starting point is really sort of traditionally, I think people when they're writing down statistical models, people looked at models that were point identified, sort of meaning that if we had a large enough data set, we would be able to figure out without any uncertainty what the values are of the objects of interest. So another way of saying it is you would write down a complete model such that in the end there's sort of a one-to-one link between the joint distribution of all the observed variables and the parameters you're interested in. And so partly we just seen that if you had a model where you couldn't figure out what the values were of the parameters, even in infinitely large samples, there wouldn't be much hope of learning much in finite samples. And sort of partly what these recent applications have shown, and so in general this approach has shown, is that even in cases where we can't learn exactly what the value of the object of interest is in large samples, we may still be able to learn a fair amount even in finite samples. And so what I want to do in this lecture is sort of give some examples that make that point and argue that they suggest we can learn interesting things. That in a lot of cases it is useful to think about relaxing some of the assumptions that actually make the model point identified, where these last few assumptions are often very dubious ones, don't have much credibility. And so rather than make those assumptions and sort of hold your nose, kind of try to see what you can do without making those last couple of assumptions and see if there's still something we can learn. And so in a lot of cases, it turns out you can't learn very much, but there are certainly a lot of cases where you can learn something of interest. And then in the last part of the lecture, I want to talk a little bit about inference. And so there's sort of a couple of issues that have come up in the theoretical literature. First one is sort of given that we're not point identified, meaning that in large samples, infinitely large samples, at best we can the best we can hope to find is a set of values that is consistent with the model and consistent with the data. How should we think about confidence sets? So there's two views. One is that even though we can't identify the parameters, we should still look for confidence sets for the parameters themselves. So in the end, even if we can't learn what the value of the parameter is, there is some parameter out there that we're trying to get at. We're trying to construct a confidence set for that parameter, just the same way we do in point-identified models. The second view is that we should get a confidence set for the set itself. It's a confidence set that includes the entire identified set with some fixed probability. So that I don't quite understand why that second thing is of interest, but there's other people who disagree with that, and so I'll try and illustrate what the difference is between the two, and why I think we should be interested in confidence sets for the parameters rather than for the set itself. Second point is there's sort of, in a lot of these cases, there's concern about uniformity of inferences. What I mean by that is that we'll be trying to maybe be interested in constructing a confidence set or confidence interval, and we want to be sure that that confidence interval does well uniformly over in some parts of the parameter space. And in particular, sort of some of the proposals for confidence intervals that are out there do badly when the model is in fact point identified. And so it turns out that sort of, and I'll give some examples to make that clear, but it turns out that they're actually narrower than confidence intervals would be in the point identified case. And that sort of clearly doesn't make any sense. And so that suggests that we should be concerned about uniformity of these uniform coverage of these confidence intervals. And so that's led to some modifications and some outstanding questions for doing inference in these settings. Okay, so the first thing I want to do is just discuss a bunch of these examples. The first one, sort of statistical one in a sense, is not of particular substantive interest, but it illustrates a lot of the issues very well. And so I'll come back to this example when we're talking about inference. So this is just a missing data problem. We're interested in the population mean of some random variable y. We only observe y if d is 1. We don't observe y if d is 0. We always observe the missing data indicator d. And so setting this up, letting p be the probability of observing y, so the expected value of d, letting mu1 and mu0 be the conditional expectation of y given d is 1 and d is 0. And you can think of the parameter of interest. You can write the parameter of interest as theta is p times mu1 plus 1 minus p times mu0. Now, what part is the data informative about? In large samples, we can estimate p consistently. We can estimate mu1 consistently. There's nothing we can learn about mu0 from the data. So if we don't have any information about mu0, if we don't have any information about the distribution of y given d is 0, there's nothing we can say about possible value about the range of values for theta. Even if p is very close to 1, even if there's only a very small amount of missing data, if y could be extremely large and extremely small, then there's no limit on the values that theta could take. So in this case, the whole real line, all real values would be for theta would be consistent with the data and well, calling this a model is a little bit of an exaggeration, but all values of theta would be consistent with the data. Now, suppose in fact we do have a little more information. Suppose that y is binary, then clearly mu0 has to be between 0 and 1. And so this actually gives us potentially informative bounds on theta. Now there's no possible way that theta could be less than p times mu1, which corresponds to all the missing values being equal to 0. And there's no possible way it could be greater than p times mu1 plus 1 minus p, which corresponds to all values of mu being equal to 1. Now, so this is so this is pretty much the simplest case of these problems. But let me still make a couple more comments on this. Here, in this case, these bounds are sharp. There's no way we can get better bounds on theta without additional information. Another way of saying that is, for any value of theta in this interval, we can find a joint distribution of y and w that is consistent with the observed distribution, with the joint distribution of the observed data, and consistent with that particular value of theta. So here, without any additional information, this is the best we can do. And if p is in fact very close to 1, this would be a very narrow interval. We would learn a lot, but obviously if p is very small, we wouldn't learn very much in this case. Now, there's another way of getting informative bounds instead of looking at the case where the random variable itself is bounded. Suppose we're not interested in the mean of y, but we're interested in the median of y. Then defining q sub tau to be the tau quantile of the conditional distribution of y given d is 1, we can find bounds on the median of the marginal distribution of y. Lower bound here is the 1 over 2p quantile of, an upper bound is the 1 over 2p quantile of the distribution of y given d is 1. A lower bound is the 2p minus 1 over 2p quantile of y. And you get a range of values consistent with the median by essentially imputing very large or very small values for the missing y's and calculating the median under each of these extreme scenarios. But again, we end up with an interval that, depending on what the data look like, could be more or less informative, and especially if p is very close to 1, this could be a very narrow interval. Now, you can do that, and I'm just setting this up because I want to build on that in one of the later examples. Here, if p is less than a half, you wouldn't be able to learn anything about the median without having some bound on the values of y. But in general, if p is greater than a half, you would get you get a bounded interval irrespective of the marginal distribution of y. You can extend that to look at any other quantile, and you get the identified set that is given on the slide there, where you get a potentially informative, well, it's a generally informative lower bound and upper bound on the theta quantile of the distribution of y. Now, let me move on to a more substantive example, which is from a paper by Mansky and Pepper. So Mansky and Pepper are interested in estimating the returns to schooling. And so they start with an individual. They want to allow for a lot of heterogeneity. And so they start with an individual level response function y sub I of w, where for each value of w that measures the log earnings that a particular individual would have received had their level of education been equal to w. And what they're going to be interested in is the average return of moving sort of randomly selected individuals, or moving the entire population from some schooling level S to some schooling level T. So if we just look at this for values of S and T that differ by 1. And if we assume the effect of schooling is constant for every year and for every individual, this would just be the regular returns to schooling. But here they want to allow for heterogeneity in the level of schooling as well as heterogeneity in the returns to an additional year of schooling. And so the object of interest is these differences, delta S and T. What we observe is actual years of schooling, WI, and the realized earnings, YI, evaluated of WI. Now, if you're willing to make an heterogeneity or unconfoundedness type assumption that conditional on some set of covariates, W is independent of YI of W, so that the level of schooling that someone gets is unrelated to the unobserved components of their earnings, then we would just be able to estimate delta of S and T for all values of S and T, at least if there's enough support. But that clearly is a very strong assumption. So this has been the subject of a huge literature. Sort of early work by Griliches. I think a couple of years ago there was a paper by David Card kind of surveying that literature. There have been lots of interesting identification strategies for trying to get at these questions. And so what the approach Mansky and Pepper take here is to try to relax this assumption and just make, without relying on additional information that would get you to point identification, see what we can learn about delta of S and T under arguably much weaker assumptions. And so two of the assumptions they consider, and the ones I want to discuss here, first, they assume that increasing the level of education does not decrease earnings at the individual level. So for a particular individual I, if you increase their level of education, their earnings may stay the same or they may go up, but they cannot go down, and that holds not just for sort of on average, that holds for each individual. And so the second assumption is what they call monotone treatment selection. If we compare individuals, we choose a particular level of education. If we compare them with individuals, we choose a lower level of education. If we compare average earnings at a fixed level of education, it's always going to be higher for the first, or it's at least as high in the first group as it is in the second group. So think about this in terms of ability bias problems. If we think that individuals with higher ability choose higher levels of education, this essentially amounts to assuming that expected earnings increase in ability, but it's not imposing functional form or linearity type assumptions, assuming that this is dominance relation between the two groups, that individuals who choose a higher level of education on average have higher levels of earnings at each value of education. And so both assumptions, you can argue about, certainly assumption 1 is very strong in the way it imposes this at the individual level. And so at some level, this is clearly not a credible. This is still not a credible assumption. It's saying that no individual would be harmed by having more a higher level of education. And clearly, if this takes away from labor market experience, that is which is the form this assumption is making that claim, that is certainly not credible for all parts of the population. But at the same time, it clearly has captures a lot of features of why we think simply comparing earnings for individuals with different levels of education may not give credible estimates of those returns. And so what Muncie and Pepper then do is take these two assumptions combined with the joint distribution of earnings and education and see what they can learn about the returns to education. And so sort of it's somewhat messy and not particularly interesting calculations show that in the end you can get a lower and upper bound on the expected value of earnings given a particular level of education, which is given here on this slide. That in itself is still obviously not particularly informative, but if you apply this to the returns in going from 12 to 16 years of education, they find an upper bound of 0.397. Now, sort of to put that in perspective, if you divide that by 4 and look at the implied average yearly returns, this gives us about 0.1. And so this actually gives us a somewhat, arguably, informative number, upper bound on the returns to education, if you're willing to believe these two assumptions. Now, and I'm actually not sure whether this is in the paper or not. They don't. I certainly don't recall what the lower bound is under this set of assumptions. And if you actually look at these assumptions, they're very much geared towards being helpful for upper bounds. So I think actually what I recall, and certainly I've seen these numbers at some point, the lower bound for this number is unbelievably large, negative. So you certainly don't get a particularly tight interval here, but you get an arguably informative upper bound. And the reason for making that comment is you do have to keep in mind here that once, I'm only giving you the upper bound here, but once you have an interval, you cannot. You cannot interpret it at all sort of as a standard confidence interval where you sort of think the midpoint is at some level the most plausible value. Here, if you take the midpoint of the interval for delta 12-16, you still get a very large negative number, which clearly doesn't make any, which is extremely implausible. Sorry, actually, you get 0 here. Under this, it's under a different set of assumptions that you get a negative number. Here, it's by assumption the returns are non-negative, so you always get 0. But the interval itself does not have the interpretation that the midpoint is plausible here. But the main point of this example is that under sort of clearly a very different set of assumptions than sort of standard exogeneity or instrumental variables type of assumptions, we actually get a remarkably informative upper bound on the returns to education. Same time, the data here are not informative about the lower bound. The lower bound just comes directly from the assumptions that earnings go up with education, and so we get a lower bound of 0. Okay, second example, sort of third example. So here is one of the Tamer papers. This one joined with Bo and Array. What they're looking at here is a problem that was sort of viewed as somewhat intractable, sort of prior to this this partial identification literature. Looking at a problem sort of at a nonlinear panel data model with a binary response variable, where sort of the latent index is linear in the lagged outcome, and there's an individual specific effect alpha I, and a idiosyncratic error epsilon it. The interest here is in gamma. So given this part of the model, given that we first write down the equation that sort of characterizes YIT, given the past and given the covariance, suppose we also are willing to postulate a parametric model for the random effects, and that could depend on the axis. It could be independent of the axis. Then that's still not enough to identify gamma. Gamma is the focus here. The only thing that is missing is a model for the conditional distribution of the initial condition, given all the covariates and given alpha I. And that's sort of an awkward thing to specify. So there's a large literature. There's a little discussion of this in Jeff's book. It's sort of an awkward distribution to specify, because you'd like to specify it in a way that's sort of coherent, irrespective of the number of time periods you have. You would like to specify a model that would be the same, irrespective of whether you have 3 or 4 time periods. And sort of to do that coherently is a challenge. And so people have done a bunch of things, but here and in fact they've established that in fact with 3 time periods gamma is not identified here. We can't get a root n consistent estimator. In fact, we can't get a consistent estimator for gamma in this case, and so people have moved to use slightly different models. For example, in some cases, you can do fixed effect logit type things with panel data. But here, with normality, even if we have a parametric distribution for alpha, we cannot identify for gamma, which seems very awkward in a sense, because it seems so close to models that we can identify. And so partly what people did was sort of change things slightly to get back to identification. But what Honoré and Tamer here did was try to figure out whether even if we can't identify gamma completely, whether we can still learn something about gamma. And so what they do sort of in their paper, they see if they take a particular fairly flexible distribution for alpha, where they make a discrete distribution with a finite and known set of support points with unknown probabilities. And what they do then is try to find the range of values of gamma consistent with the data generating process. So they actually just do and they only look at the identified set itself. They don't focus on inference. But what they find is that, so in this case with t equals 3, where it was known that gamma wasn't identified, they find that depending on what the value for gamma is, the width of the identified set can in fact be 0. And even if for values of gamma different from 0, the width of that identified set is typically very small. So here, this is a figure taken from the Honoré Tamer paper, where the dark area, so the x-axis is true values of gamma, and then for each value of gamma, it shows you what the set of values of gamma is that is consistent with the data generating process. And so if gamma is equal to 0, we can in fact identify that, but even if gamma is minus 1 or 1, the identified set is very small. And so in this case, and this is really the main point I want to make with this example, even though the identification here is very hard to come by with using this partial identification analysis, you can actually get potentially fairly precise inferences. And the fact that this set isn't a point, but is actually an interval, shouldn't really matter once you try to estimate all this with sample data, there's going to be a lot of uncertainty there, and that probably swamps the uncertainty coming from the width of the identified set. Okay, the fourth example, which is from a different paper by Tamer, this one joined with Phil Hale. They're looking at auction data. So they're looking at English auctions. So the idea there is in the auction, bidders keep increasing their bids until there's only one bidder left who gets the object that's being auctioned off. Suppose Hale and Tamer focus on sort of model this as a symmetric, independent private values auction. And so what they're interested in, and so they're assuming that they have data from a large number of auctions, each with a number of bidders. And for what I'm doing here, I'm just going to assume that the number of bidders in each auction is the same. Each bidder has a value drawn from some distribution, here denoted by f of nu and of f of nu. This distribution, this value distribution, is the same in each auction, and in fact, Hale and Tamer have a more general and more credible model where there's covariance in this as well. But the idea is that somehow there's a component of this value distribution that is the same across all these auctions, and that you're trying to estimate by using data from multiple auctions. And so, in the theoretical literature, sort of people have sort of thought about having this type of auction where you actually see for each bidder whether they're still in the auction or whether they've dropped out. So at that point, you would be able to infer for each bidder what their value was. Each bidder would actually drop out at the point where the bid exceeded their value. And so if you observe that for each bidder, you would just directly get these observations from the value distribution, and you can estimate the value distribution. Now, that's never what you actually observe in these auctions when they actually do these things in practice. What you see is someone makes a bid, then someone else makes a bid that goes up by some discrete amount. The current bid doesn't go up continuously. And you don't really see for a particular bidder when they're still in the auction or whether they've dropped out. If they subsequently make a bid, you know their value must have exceeded that number. But if they don't ever bid again, you don't know at what point the bidding exceeded their value. And so what Hale and Tamer are interested in is trying to figure out what you can learn about the value distribution in that setting, where what you see is this sequence, this sort of finite number of bids, and the identity of the bidders, but you don't see when people actually drop out of the auction. And so the key assumptions they make in order to get some sense of what the value distribution is, and these both seem very reasonable in this setting. First of all, is that no bidder ever bids more than their valuation. If they do, then I guess they would then pretty much anything goes. And the second one, that may be slightly more restrictive, but it still seems very reasonable. No bidder will let someone else win the auction if the winning bid is actually lower than their valuation. So if in the end person I wins the auction, then it must be that there's no, with a price of 80, it must be that there's no other bidder with a value higher than 80. And so given those two assumptions, they show how you can construct both upper and lower bounds on the value distribution. And so here, these are conceptually very simple. Suppose that the highest bid for participant I in the auction is B sub I, then since nobody bids more than their value, for nobody the value of their bid is higher than the actual value, and that gives you an upper bound on the distribution, on the value distribution. Then the second part is that they get a lower bound on the value distribution, sort of using the second assumption. Given that the fact that no one walks away if the winning bid is less than the valuation, it must be the case that the second highest of the values among the end participants in the auction must be less than or equal to the winning bid. We observe the winning bid, and so we can get the distribution of winning bids over all these auctions. That gives us a bound on the distribution function of the second highest order statistic. Having a bound on the second highest order statistic gives a bound on the distribution function that the order statistics came from. And so that gives us the second bound on the distribution function. And so together they give us an upper and lower bound on the distribution function. Okay, and so this is going to be the fifth and last example, and then I'm going to make some comments on the theoretical part, on the econometric part of this. So this is another, and there's a bunch of papers looking at partial identification in this setting. And so one is the paper by Siliberto and Tamer, but there's also work by Andrews, Berry, and Xia. There's a paper by Pecos, Porter, Ho, and Ishii. So I'm just taking it's essentially a very simple version that is a special case pretty much of all these papers. So here, suppose you have two firms that contest a set of markets. So it could be different pairs of firms contesting sets of markets. In market M, the profits for the two firms are alpha A plus delta A times an indicator whether firm B participates in that market plus some idiosyncratic component. Same for profits for firm B in market M. And the decision whether to participate in the market depends on whether profits are non-negative. So that seems all fine. And so we're assuming here there's complete information. Every firm knows everything about the other firms. So the complication is that this doesn't really specify the decisions completely. In the terminology of this literature, this is an incomplete model. For some pairs of values of epsilon A and epsilon B, there's two solutions that satisfy the natural equilibrium conditions. There's two solutions that satisfy these conditions on participation, namely sort of for intermediate values of epsilon A and epsilon B. The solution is that one of the firms should enter, but not both. But it could actually be, both would be maximizing profit given behavior of the others if they do the opposite of what the other firm is doing. But so far, I've not specified whether under what conditions the data would be 0-1 versus 1-0 in this case. And so what is argued in this literature is that it's very difficult to specify in these multiple equilibrium settings which of these equilibria you would actually observe, or which equilibrium would actually arise. And so here, these partial identification strategies are being used to remove sort of the one assumption they don't want to make, namely the selection of the equilibrium. And so just to illustrate this, this is a figure essentially from Siliberto and Tamer's paper. For intermediate values of epsilon A and epsilon B, you get this indeterminacy where you could have one of these two equilibria, where for all the other areas you would get a unique equilibrium. So what is the implication of that? Another way of thinking about this is that for once we have distributional assumptions on epsilon A and epsilon B, even given the parameters alpha A, delta A, alpha B, and delta B, we can't write down the probability of a particular outcome, because it still depends on this unspecified equilibrium selection mechanism. So it still depends on how we select, in these cases where profit maximization is consistent with one of the two firms, with either one of the two firms participating as long as the other one doesn't. We haven't specified how that they get selected, which means we get a range of probabilities of the outcome 0, 1 that are consistent with the model and with the data. So if you do that, if you write that down for all four outcomes here, what you end up with for all four situations is an upper and lower bound on the probabilities. Actually, for the first and the last one, the upper and lower bounds would actually agree. But sort of, it's useful to think about this in general as this type of model generating not moment conditions of the type where we have an expected value of parameters that is equal, so expected value of some function of a random variable and parameters that is equal to 0, but we have an inequality where probability, and so it's something that we can write as an expectation, is bounded by a function of the parameters. And so sort of a general way of setting up these problems is by thinking about problems that can be written in this following form, what I call here the generalized inequality restriction form, where we have a known function of a bunch of random variables and a parameter that is non-negative, where sort of the traditional method of moments setup refers to cases where this expectation would be equal to 0. So this fits this Siliberto and Tamer example. It fits a whole bunch of examples, and a number of papers have studied estimation and inference kind of in this particular setting, which seems a very useful sort of general framework for thinking about these problems. So in particular for estimation, there's this work by Chernosikov, Hong, and Tamer. We try to develop methods for estimation and inference in this setting. So you need a little bit of explanation here. So for a particular vector x, the vector in brackets x plus or minus refer to the component-wise positive and negative parts of that, so that you can write as x in brackets minus plus x in brackets plus. And so what they do then is suggest is look at this population objective function, the negative part of this of the expected value of this moment function psi, the inner product of that with some weight matrix w times again the negative part of this expected value of this function psi. So this is a useful way of characterizing the problem, because now for all values of theta in the identified set, we have q of theta equal to 0, and for theta not in the identified set, we have q of theta positive. So the natural thing, sort of analogous to the standard generalized method of moments, would be then to take that function and look for the values of theta that set that equal to 0, or that minimize that, that doesn't quite work because even if there's a set of values for which the population objective function is equal to 0, there may be actually, let me step back a bit. There may be no values of theta for which the sample equivalent to that is equal to 0, and in fact there may be very few values for which it's minimized, and just minimizing this is not going to give you consistent estimates of the identified set. So what Janosikov, Hong, and Tamer suggest then is estimating the set by looking for all values of theta such that the sample objective function is below some sequence of values alpha of n, where alpha of n is going to 0 at the appropriate rate. And so this is sort of partly where this literature is still very much in flux. This certainly seems a very promising way to go, but it hasn't it hasn't been tried out a lot in practice. Now, the last part I want to do in this lecture is look at inference. And so here there's actually been a lot of work in the last 5-6 years, a lot of it by Mansky, by students of Mansky's. So the first question is whether we're interested in a set that includes each element of the identified set with fixed probability, or the entire identified set with that probability. And so the first condition would be that for all values of theta, you would need to be in the confidence set with some probability. Second one requires that the whole set is in that confidence set. Second one is much stronger than the first, and so generally you would end up with a bigger confidence set. As I said before, I think this is sort of, there's no particular reason why you would need to have a confidence set that includes all possible values in it with fixed probability, rather than each separate possible value with fixed probability, which is much more analogous to Stanford standard confidence intervals. But there's been some discussion about that, and there's not necessarily complete agreement on that. Now let me look at sort of two issues there in estimating these confidence sets. And so I'm just going to focus on the case where we're interested in confidence sets for the parameters themselves. So going back first to the missing data example. So we're interested in the identified set is p times mu1 is the lower bound, p times mu1 plus 1 minus p is the upper bound. The only thing we don't know here, if we assuming the probability of the missing data is p is known, the only thing we don't know is mu1. It's obviously very easy to construct a standard confidence interval for mu1, and so that can be used in three ways to construct a 95% confidence interval for theta. So the first one is just to take the lower bound, the lower confidence bound for mu1, plug that into the lower bound on the identified set, and take the upper confidence bound for mu and plug that into the upper bound in the identified set. So that's the first suggestion there. That's going to be conservative. It's going to be conservative in the following way. For every value of theta in the interior, the coverage rate is going to be 1. For either of the two bounds, as long as the probability of the data missing is greater than 0, or the probability of observing the data is less than 1, the coverage rate is not 0.95, but 0.975. In some sense, if the interval has non-zero width, you only have to worry about errors of one type, because errors on the other type are still going to be in the identified set. So you can fix that problem by just changing the quantiles of the normal distribution you're using there, and replace the 1.96 by 1.645. And so that gives you point-wise a 95% confidence interval. But now the problem is, if in fact p is equal to 1, if in fact we point identified and we observe the y with probability 1, then this confidence interval doesn't give you the standard thing back. It gives you a standard 90% confidence interval rather than a 95% confidence interval. So in cases where we're very close to point identification, this is not going to work very well. And so what has been suggested in work I did with Mansky is to modify this a little bit depending on sort of an estimated version of the width of the confidence interval, adjust the critical values a little bit in a way that if the width of the confidence interval of the identified set is big enough, you're going to get to this tighter interval based on the 1.645 critical values. But if the identified set is very narrow, you would get back to the standard interval sort of in a smooth way that you get coverage that is uniform over all values for P. And so the last problem, and so this is much more, this is very much an area where things are still in flux. So I want to just look at a very simple example of this setup with inequality restrictions. And so suppose we just have two random variables. We know that both of them have expectation greater than theta. And so the identified set here, if we know that theta is non-negative, the identified set here would be the interval from 0 to the minimum of mu1 and of mu of x and mu of y. And so the difference with the previous example here is that by having the upper bound be the minimum of two unknown parameters, where obviously we're going to estimate these two means by sample averages, but we're going to have to get into the problem that the minimum of these two things is not going to have a distribution that is very well approximated by a normal distribution if the two population means are very close. So what do I? Let me sort of make that point slightly differently. So the naive interval, 95% confidence interval, would be to take the minimum of, suppose these two random variables actually have the same variance sigma, and we have sample size in both cases of n. A naive confidence, 95% confidence interval would have an upper bound equal to the minimum of x bar and y bar plus 1.645 times sigma over and that should be over the square root of n rather than over n. And so essentially what it's doing is ignoring the moment condition that is not binding. So we have these two averages, x bar and y bar. Essentially here, this confidence interval ignores the average that is too big, that is bigger than the other one, and constructs an interval that would be the natural and the appropriate one if all we observed was x bar. I suppose that was the smaller one. And that's sort of fine. That's going to give you 95% coverage asymptotically, point-wise, sort of under two conditions. One is that the minimum of these two things is actually positive. Otherwise, you get this problem that I addressed on the previous slides. But you also need to have that these two means are not too close together. Essentially, what I mean by that is if you need to be sure which of these two moment conditions is actually binding. And so where this gets into trouble is in particular in cases where you have a lot of inequality restrictions and you don't know and you can't tell from the data which ones are actually binding. And so here I just tried to illustrate this problem with a case where there's just two inequality conditions. But sort of the type of problems Pekis, Porter, Ho, and Ishii talk about the concern about cases where they have a large number of inequality restrictions and they can't really tell from the data which ones are binding and which ones are not. And so you need to take into account the uncertainty coming from not knowing which of the moment conditions are binding. And that's going to give you trouble with this type of confidence interval. And so the formal version of that is that these confidence intervals are only going to have the right coverage point-wise asymptotically, but not uniformly. And so in practice, that means they're not going to work very well. Now, there's a couple of ways around that. And there's some ways of constructing conservative confidence intervals by essentially taking into account more moment conditions than you need to. But there do seem to be some ways of constructing confidence intervals that do ignore the irrelevant inequalities asymptotically, but without getting into trouble with this uniformity problem. And but the only thing I think that's been shown to work so far is subsampling, where there sort of is a variation on bootstrapping, but where standard bootstrapping doesn't work, but subsampling, where you only take subsamples of the original data set, does seem to work. But so the main point at this stage is that sort of this setup in terms of inequalities seems a very natural one, a sort of very general one, but there's still some outstanding questions with the inference. But it does seem that this setting is actually fairly relevant in potentially in a lot of cases. Okay, that's it for this one. Are there any questions? Yes, David. Yes, yeah.
And so think of like male-female labor suppliers, things like that. Is there any work on whether you're actually observing an incoherent model, or if there's like a family utility function that's generating a coherent version? So in the entry example, it would be like, is there a cartel going on? Like statistically, has anybody tried to figure out whether you can tell whether you really have an incoherent model or not?
Well, no, so I think sort of my reading now of that literature on the incoherency problem was that people were just very concerned with the fact that what this was, it was essentially an incomplete model, that even knowing the values of sort of that we typically think of, you know, the unobserved components, that tells you what the outcomes are going to be, and that somehow was a necessary condition for a model to make sense. And the label that was given to that concern was that these models were incoherent. I think now that is just a misnomer. These models were not incoherent. They were incomplete. People didn't specify what the household bargaining model was, and maybe they were right that it was difficult to specify. But the way those models were dismissed in the econometric literature as just not being coherent, not making sense, I think was wrong exposed. And it, yeah.
I'm asking a question. It seems like the implication of, say, Nash behavior is multiple equilibrium.
Yeah.
So if you knew there was for sure multiple equilibrium, that would say for sure it's not a cooperative type model. So there's kind of that's a result that's known in the family of our
Yeah.
behavior.
Yeah.
Okay, so is there a way to test whether there's a result? What I'm trying to ask is if you found that the interval, the identified sets kind of collapse the points, would that be consistent with there not being multiple equilibrium? I realize
Yeah.
in IO the multiple equilibrium thing is natural, but in
Yeah.
labor economics that's not the case. It's quite important whether we have Nash bargaining households or not.
Yeah. So I think certainly in some cases it's going to be possible that these identified sets are inconsistent with other models, and so that you can get testable implications there. I'm not completely sure sort of how informative, sort of whether these tests are always going to be informative, but I think that's an extremely interesting question, and that sort of these. I've only really seen some of these so these entry type, also these binary response models in I/O. But certainly the original literature there was in labor, and I think it would be very useful to revisit some of that. I think